Hi, this is Matt McCormick. I'm in the Department of Philosophy at California State University, Sacramento. This is my second lecture on the Turing Test for my Philosophy of Mind Phil 153 course. And we've moved from the first question of the first lecture uh, about consciousness inside a machine, and now we're wondering how can we build a conscious machine. Turing got us started on this question, and now, especially in the last 20 years, there's been an enormous development along these lines that's showing great promise to producing I'm going to call them a Turing machine. And by a Turing machine, I mean a machine that can pass a robust Turing test. That's not the way Turing described or labeled the machine, but for our purposes, it'll work. So just know that if you hear someone else talking about a Turing machine, they're probably talking about one of the original computers that he built in order to help the English decrypt Nazi secret messages during World War II. Okay, so we're thinking about a more robust, expanded, sort of philosophically um, important Turing test of this sort. Suppose we build a machine that responds in compelling, intuitive, believable ways to all of our questions and inquiries about its having internal, subjective states, personal life, aspirations, goals, ideas, questions, thoughts, desires, and beliefs. And it seems to be aware of us as beings with minds, beliefs, goals, and so on too. So imagine a machine that can engage in a completely compelling, ordinary human conversation. A really great example of this, another great movie reference. Go back to Stanley Kubrick's 2001: A Space Odyssey, and HAL 9000 is a sort of classic science fiction example of an AI system that has all those capacities. HAL has full-blown, um, detailed, nuanced, layered, self-aware conversations with the crew. Hal knows what he doesn't know. He knows what they know and what they don't know. He understands their motives. He can predict what their behavior is going to be. He knows what he doesn't know, what he needs to find out, and so on. It's a really remarkable portrayal. So the question then is that machine conscious? That's the question I want us to get to, which is not the same as the questions that Turing was asking in the original 1950 paper. Okay, so computer scientists, AI researchers have been working on this problem for decades. The modern pursuit, AI research programs have been at work on this, at least since the 50s. Turing built a machine, sort of or built one of the first computers in the 1940s. Those, we're going to call those, or I want to describe some of what was going on there. And what was going on there was attempts at early NLP, or natural language processing. Because that's what we're doing when we're having a conversation, is that you're processing natural language. You're listening to my sentence, and you recognize that it's a question, or you recognize the subject and the verb, and you process it all this effortlessly, and you understand what the sentence means. That is, you understand what the sentence means. There's a subject, a verb, and an object. You understand meaning. So there's a structure to all of that. And our early attempts in AI research to try to build a machine that could do something like what Turing had in mind were these early rule-based attempts and symbol-based attempts at what we learned in a previous lecture as Gophi, good old-fashioned artificial intelligence. So since Turing, we've been trying to build these sorts of machines. And these machines have hand-coded, deliberately coded rules for sentence structuring. How do you put a sentence together? They have very limited domains. There's typically very little they can talk about because the range and the memory storage and the amount of topics they can talk about has to be limited by computational storage and speed, processing speed. And they often employed Noam Chomsky style deep grammar assumptions about the deep structure of how sentences work. And we haven't read any Chomsky, but Chomsky had this huge impact on linguistics in the mid 20th century. discovering or for unpacking, describing what he called the deep grammar, which is the structure of all human languages. So another couple of examples of online chatbots that you might look at are Mitsuku and Eugene Guzman. I mentioned that one before. And those have more or less, they follow this Gophi approach, the rule-based procedure for having conversations. And what you'll see when you go talk to one of those two chatbots is that they don't work. They're very limited, and it's pretty obvious very quickly that the thing has got limits, and it doesn't seem like it's conscious, doesn't seem like it's thinking. Another early famous example is this ELIZA. ELIZA is actually a sort of psychotherapy program that asks interesting questions like, is something troubling you? What is the connection, do you suppose? Can you think of a specific example? Um, is it important to you that your boyfriend made you come here? And ELIZA has these kind of canned responses that just keeps asking questions. And sometimes people actually felt sort of edified by talking to ELIZA. There's a famous example where somebody doesn't really understand what's going on and they have a kind of meaningful discussion. But that's not like an aggressive, serious Turing test or Turing test interrogator. Okay, so this Gophi or logicist approach, which also fits in with the discussion in previous lectures I had about Chomsky and Fodor and about attempts to understand the structure of the mind, have a particular kind of approach. They use Chomskyan deep grammar, which parses language at the sentence level into basic linguistic components. It finds the grammatical syntax. Is the verb in parallel? Is the tense correct? And you can see some sort of a classic diagram of Chomskyan deep grammar in that picture. So suppose we had a system like one of these chatbots online that can have a completely grammatical and content matching conversation where it seems to be talking to you in grammatical sentences like a normal conversation. Would that sort of system, would we think that it understands what it's talking about? Will we think it's thinking or it's conscious? And I'm not conflating all those. Excuse me, I'm treating those as three different things. Does it understand what it's talking about? I think most people, if you asked them that question, they'd say no, it doesn't understand. It's a machine with syntax but no semantics. It's just following some procedural rules for cranking out outputs. And that's all there is to it. There's nothing more philosophically significant about the cognitive states or what's going on internally. At the very least, it would seem that it needs to be connected to real objects more or somehow connected to the real world. And we'll get back to that point when we talk about Searle's Chinese room argument next week. Okay, so also the Gophi logicist approach employed these banks of canned responses, and you can see that if you go look at some of those chatbots. It has a very primitive ability to parse sentences at the subject-verb level. It wouldn't be very hard to construct a sentence that would confound them or mess them up, even one that's grammatical, because it's actually a really remarkable thing, which you can do when you read a passage of text and there's a long, complicated sentence. Getting clear on the structure and the relationship and the understanding, how the sentence works is very hard, very difficult to program that. At best, at least during the Gophi era, the best that systems could do is only handle very simple, sort of straightforward, declarative, short sentences. These were hand-programmed systems. They had the hand-programmed ability to ascertain the subject in a range of suitable responses. So what I mean by that is that you've got programmers who sit down and they imagine all the possible conversations that this program could have. And they write them out and they work out in specific detail. If you get this response, then you say this in return. And then if you get this response or this response or this response, then you give these returns. So they actually carve out and hand program all of the possible conversations the thing could have. And you could see how very quickly you're going to hit a limit here. There's, you could have, hundreds or thousands of programmers working on this thing all day, every day for years. And still, I put me up against that system. And all I got to do is think of a novel topic or a strange new way to form a question, and a way to ask a grammatical and sensible question or sentence that diverts outside of the range of the class of pre-programmed conversations that these programmers put into the system, and I will make the thing blow up or make it, throw it'll have a glitch or an error message, or it'll give some otherwise ungrammatical or strange or counterintuitive response. Not hard to do that for one of those systems. You might notice also, though, it's not too hard to mess up your roommate either with a hard question or a strange way of putting something. So we keep in mind that we want a Turing test criteria that will let people in, but will successfully sift out the artificial systems that are not conscious. And these ones doesn't seem to be probable that they're conscious. Conversation programs with limited domains, and they have structures and topics. They're very strange, a very small domain of things of which they can talk about. Sherdloo is a famous example that Terry Winograd built at UC San Diego, and it did pretty well for what it did, but it was confined to a very small box full of some blocks. It had a red pyramid and a blue cube, and it could answer some simple questions about whether or not the red pyramid was on top of the blue cube and things like that. So by limiting the domain, you could sort of confine the combinatorial explosion of processing you had to do about all the possible topics. It seems implausible that these things are understanding or comprehending or thinking in any really robust sense of the term. Now, Terry Winograd might take issue with me, and some other people in AI research would have. Certainly they would have 30 years ago, but now with the new artificial neural network revolution, there's some very different things happening, and some people have got the horizon has been moved far out by new computer capacities. We'll get to that in just a second. Okay, so it turns out, of course, that natural language processing is really, really hard. Go read a passage of Shakespeare and get back to me. You'll see exactly what I mean. A passage of Shakespeare is grammatical, it's coherent, it makes sense, but it also has 10 different sort of plausible interpretations. It's very dense and complicated and very layered, and it takes a lot of work to unpack it. And that's just one example. The number of possible conversations that you can have with somebody is just staggering. In order to pass, one of these systems would have to deal with the number of natural language responses that it would have to be able to produce or to comprehend or to sort of process to deal with is just staggering. Like, imagine the number of possible conversations that you and me could have. I mean, I can think of 1,000 different topics, and we can go in 10,000 different directions on any one of those topics, and you could follow along just fine with me, or I can ask you questions about something you're doing, and I could pursue and discuss, and we could chase this sort of discussion down into 10 or 100 or 500 responses. The computational problem here is really big for making conversations. There's a recent famous example of a new AI system. The most recent one's called AlphaGo Zero, that some researchers at DeepMind, which is now a subsidiary of Google, and their leader or their CEO, Demis Hassabis, built a computer program that could play Go. Go is a really popular board game in the East. It's much more complicated in many ways than chess, for example. A Go board is bigger. In chess, the branching factor, which is a way of talking about the number of possible legal moves that you could make next. I think the branching factor for chess is like 20 or 50. Like at any given point in the game, how many legal moves could you make as white from the current state of the board? And that averages to be just a few dozen. For Go, the number of possible legal moves that you could make next is on average 250. So that means that if I'm looking at the game board and I'm imagining making this move out of 250, then now I have to picture the 250 possible responses that you might make to that move. And I narrow those down to a handful of more or less likely ones. And then I picture how I would respond to that move. And then I picture how you would respond to that move, and so on. Now, very quickly, my ability to successfully or reliably predict what you'll do 3 moves into the game just gets swamped by the number of possibilities. The branching tree of the number of possible future games here is just, it's staggering. It just goes out to infinity very quickly. So when I'm playing chess, or when we're playing checkers, for instance, checkers is a very simple game. The branching factor is very low, and we can actually we've actually written computer programs that solve checkers. Like the machine can actually predict all of the next subsequent moves that you or I might make, and then it can decide which is the optimal play to make next. Only because checkers is so simple. It just moves forward and back. It's got very simple rules, and the game board is only 8 by 8, squares, 64 squares. So simple rules, small domain, very few moves. Chessboard, small domain, different pieces with different permutations on the moves they can make. A knight moves different than a bishop and moves different than a queen. And then staggeringly high number of possible games, chess games that we could play as a result. Okay, Go, vastly more complicated than chess. We now have AI systems that can play Go better than the very best human player. Those AI systems manage or deal with that branching factor not by brute force computation, not by cranking through all the possible games, but by carving and sculpting and reducing down the possible futures into ones that are more likely and ones that are less likely. That's a bit like the way humans do it. Okay, now I just say that to set up bring us back to the conversation about conversations. So now imagine or think of you and me having a conversation a little bit like you and me playing a game, except now the game board is the world, and the number of possible topics is infinite, and the number of moves that we could make with our conversation from here to there to there to there is also infinite. Okay, so that's what I mean by combinatorial explosion. There are more calculations or processing to do there if we're going to actually work through the details than any machine could possibly process. So something's got to be done to sort of solve and scale down and get the natural language processing problem into a scale that we can deal with. Okay, so what would it take to do to hold the conversation? Well, Turing was wrong about this part. Turing suggested, or at least my caricature of Turing in the previous lecture, makes it look like Turing thinks that we can just do a lookup table. And a lookup table is where we, on one axis of the table, we put all of the possible first things I could say, and then we put all the possible next things you could say, and then we work out all of the possible conversations that might therefore unfold. So a lookup table would be where, okay, if someone says hello to me, what do I say back? I go look it up, I say hello. And if they say, how are you? What do I say? I'm fine, how are you? And you look it up and you go through all those. If they say, have you read King Shakespeare's King Lear? Then I say this, and so on and so forth. Okay, well, a lookup table won't work because there's too many possible conversations that we could have next. After hello, the combinatorial explosion of all the possible conversations that could unfold vastly exceeds the computational power of all the computers on the planet, and certainly of your brain. Because that's not what you do when you have a conversation. You're not running through all the possible next conversations that can happen. Okay, so what do? Well, the way that modern artificial neural network research into this topic and the way that modern natural language processing theory works on this is they assume that we use and that what a machine needs are heuristics. Heuristics are a shortcut. They're ways to carve off or to eliminate non-starter possibilities, right? When I'm, if I've played a lot of chess, if I'm considering some possible moves for my queen, there's a whole bunch of moves that will be immediately obvious to me that that's a dead end. I don't want to do that. Don't put your queen in jeopardy. Don't put your queen in the vicinity where your queen can get taken by the opponent, the other side's pieces. And that's just like a quick and dirty rule that I use. And I use a lot of those kinds of heuristics all the time to sort of make quick decisions and make fast computational work of problem solving. Okay, so to make a natural language processor, um, contra Turing, it looks like we need heuristics for narrowing down branches of inquiry, narrowing down which sort of trees and branches we pursue out into the possible futures. We need heuristics for responding to questions. We need a system that's able to ask new questions or to raise new issues. We need a system that needs to be able to keep track of what has been said so that it needs to map or track the conversation so far. Oh, we talked about this and we're going to continue talking about this, or I have another question about this. I wanted to ask you some more about that basketball game you saw, or whatever. Keeping track of what the other speaker knows and doesn't know, believes and doesn't believe. Look, when I'm having a conversation with you and I ask you a question, who's got the best burrito in town? And you say it's La Fiesta. Okay, so now I've got a picture in my mind that you know something, you have an opinion about something in the world, and there's some things you do know and some things you don't know. I think there's another place that's down on Franklin that's a taco truck that's actually better than La Fiesta, so I suggest that to you. And now I'm keeping track that you know this new thing that I knew before, but now you know it too, and maybe I can try to get you to believe. So I'm modeling what's in your mind and what's in my mind and keeping track of reality. So there's three things here: your mind, reality, and my mind. And I'm navigating all of those to keep clear on the different states of those, the world and what we know, what we don't know. So I'm modeling the interrogator's mind, or you're modeling my mind. I'm locating myself in the discussion, and I'm keeping track of my own responses, the differences between your responses and mine, answers and questions, and so on. So it's looking really complicated, looking very difficult to solve the general problem of having conversation. Okay, so another way to understand, and I've already hinted at this, another way to understand the question or answer the question, what would it take in order to pass, is that the thing needs a theory of mind. Now, by theory of mind, I'm using it in the sense from psychology. Um, I'm not using a theory of mind where we're trying to come up with a theory about what makes up a mind. Theory of mind is a thing that humans demonstrate when they're to a certain age, and even chimps actually show it too. When humans get to a certain age, babies show that they're aware of your mind and what's in your mind and what's not in your mind. They have a theory of mind, and um, for instance, like the example in the picture I've got here is that when kids hit a certain age, it's like 3 or 4, if if um, if Smith leaves the room and I take a doll and I show it to the kid and I put it on the table and I put it under a box. So now the kid has seen the doll go under the box, and the kid has seen me put the doll under the box. So the kid knows that I know where the doll is, and the kid knows where the doll is, and then Smith comes back in the room. Well, at a certain age, the kids also recognize that Smith does not know where the doll is under the box. The kid knows there's an inside joke. I know and you know where the doll is, but Smith doesn't know. Isn't that funny, right? And you can play jokes and games, and this turns out to be great fun for little kids. Before a certain age, they can't really parse all of that theory of mind very well, but after a certain age, they can. And it turns out that chimps actually show a pretty robust ability to keep track of who knows what, when they learned it, and what the implications are of their learning it. But you go further down the phylogenetic tree to other mammals, and they don't demonstrate much theory of mind at all. We'll talk about that some more later. Okay, so when I talk to you, I keep track of what you know, what you don't know, what you've talked about, and what we haven't talked about. And furthermore, I represent a mind in your head that contains beliefs, information that's different from my mind, and that is different from the world at large. So really, one of the really crucial capacities that it would seem that a Turing successful machine would need is to have theory of mind, because it's got to track and got to parse all of that stuff. It can't just be banging out sort of referenced pre-programmed conversations. What it really needs to navigate the heuristic it needs to solve the computational problem of getting through the world and having a conversation with somebody is, well, it needs to understand minds, which is no small order, obviously. Um, this has come to be called, in philosophy, it's called the intentional stance. Dan Dennett would say, I adopt the intentional stance towards you. I attribute a mind to you, beliefs, desires, goals, wants, aversions, and so on. Okay, so what would it take? Somebody might argue that a theory of mind is not necessary, but it looks like it might be a highly efficient way to solve the computational problem. That's what I'm suggesting. There's people like Jan LeCun and some other AI researchers who are trying to see how much they can um, get an AI system to develop without sort of building in some facilities like this. But there's also a great deal of research going into how to build facilities like this into in the form of sort of innate a priori biasing or sort of probabilistic biasing. How much of that do we need to equip an AI system with to be able to set it loose in the world and have it navigate these kinds of problems or challenges successfully? And the system would have to keep track of itself, its own beliefs, its own information state, distinct from the other person and distinct from the world too. So that is, it would apply its theory of mind to itself. And that amounts to a kind of important self-awareness that the theory of mind module that this thing is directing at you, it has to be able to direct it at itself. It has to be aware of itself as an information agent, what it knows, what it doesn't know, and so on. So there's now, some important, philosophically important capacities might unfold from trying to build something that actually can solve the conversation problem. It looks like this thing might achieve a special kind or a particular kind of self-awareness that sometimes we look for when we ask about, is an AI system conscious? Okay, so suppose this thing has a way, we build a system in 20 years or 50 years. Suppose we build a system that has a way to navigate the combinatorial explosion problem. Suppose it has theory of mind or something resembling it because we've sort of built in some innate capacity to parse the world according to those objects or those those categories. Suppose it models itself with its own theory of mind for a kind of self-awareness. Suppose it then passes the more robust Turing test that we've been describing. It passes with flying colors. Are we still sure that it doesn't have understanding, consciousness, or a mind? And what I'm trying to suggest is a machine like that is now making it pretty hard to say no. It's not obvious to me that it does not have any sort of consciousness or it doesn't deserve any kind of status here at all. Those simple chatbots, clearly not conscious, but something like that, it's starting to look hypothetically more compelling. So now let me remind you about what we learned in the previous week about artificial neural networks. The ANN revolution really, I think, opens the door here. Recall how different artificial neural network systems are from what Turing envisioned. They're parallel, distributed, they're stochastic, which means probabilistic, they're flexible, they learn and they adapt. They have massive data sets from which they acquire and they grow. They have plasticity. They have graceful degradation. They do pattern completion. And there seems to be these robust or important abilities that emerge out of these capacities. And those are still pretty simple ones, but they're demonstrating some pretty remarkable abilities. Okay, so remember all of that. And remember that's very different than the kind of discrete state serial machine that Turing envisioned. The artificial neural networks we've been describing. There's no hand coding of particular responses or no programming of the conversations it's going to have. There's no canned responses at all. Machine learning algorithms use deep learning methods in order to build this thing's capacities up. The outputs are statistical or probabilistic. The outputs are based, perhaps, if we build one of these, on the millions of actual conversations. So imagine I showed you that visualization of AI systems that were being very successful at correctly identifying handwritten nines. Okay, so the way computer scientists think about this is, look, solving the conversation problem is just a very large, much more expanded version of that problem. Break it down into little pieces, figure out how it is that letters go together or how words go together, and then connect them all up and sort of structure the environment and structure the computational problems the right way. And they're going to tackle the problem and try to build a system that can do it. Um, so let me just mention one of the ways in which AlphaGo Zero does what it does. One of the ways it plays, the way it succeeds at playing Go. Back to our analogy with current successful game playing AI systems. So AlphaZero uses what's called a Monte Carlo tree search algorithm to navigate choice space. Okay, so recall that I said that the branching factor for Go is 250. From any given state of the board, there's 250 possible moves I can make from here. And then from each of those, there's 250, and from each of those, there's 250, and so on, back and forth between you and me while we play the game. Well, we can't possibly compute all of that and deal with all of those. So the Monte Carlo tree search procedure selects some of those trees and then branches and then leaves at random. And it chases down some randomly selected pathways to the future, to 10 moves out, to 20 moves out, to 100 moves out. And it confines the number of those to its computational processing limits. And then when it gets down deep into those hypothetical games, when it's looking at its possible choices, it evaluates the outcomes. If we were to chase that line of moves down into that possible future, would I win or would I lose? 60% probability I'd lose. Okay, that's not a very good branch to chase down. So it assigns an evaluation to that inquiry and then goes and randomly selects some others. Now it's limited by time and computational capacity and processing speed and so on, like you are when you're making choices. And it scales how much inquiry it makes into those accordingly. And it comes up with some rough ideas about which which moves lead into more promising futures and which moves lead into less promising futures. And on the basis of those evaluations, it then chooses back here at now which thing to do. That's very roughly, and don't hold me to this because I'm way out of my depth here on expertise, but that's very roughly the way a Monte Carlo tree search algorithm works. Now, in many ways, that's not what you're doing when you're playing chess or you're doing the variety of the things you're doing. But it kind of gives us an idea about how a seemingly intractable problem might be condensed or reduced down to something that might be manageable, and we might get some results that are impressive. Another example here is you might have seen IBM's Watson, which became really good at playing Jeopardy. And so, in fact, it became so good that it beat all the best human players. So Watson, if you don't know about Jeopardy, Jeopardy gives you the answer to a question, and the answer they give you on the board, that's these blue squares on here, are often they've got puns or double entendres, or there's jokes, or there's oblique references, or there's weird, sort of linguistically strange references that hint at the right answer. I mean, a really easy one here. He came to power 34 days before FDR and left it 19 days after him. Okay, so now I sort of run through something in my head and think about FDR. Okay, that's Franklin Delano Roosevelt. I know that. So now I might figure out, well, when was Franklin Delano Roosevelt? And then I imagine somebody came to power, so that means it's an authoritarian dictator or somebody who was roughly concurrent with FDR. Well, now I can find it. I can figure out the answer, right? I don't remember it off the top of my head. But some of these others are much more oblique and much weirder. Look at the right one on the right. When translated, the full name of this Major League Baseball team gets you a double redundancy. That's a pretty complicated, tricky clue, and it's a pretty complicated natural language processing feat to figure out the answer to that. I don't remember the answer to it. I wish I should have known for this discussion. Okay, so first point to make here is that this is not a Turing test machine. It wasn't designed for that. It was just designed to play Jeopardy well. It's also, I think, not exactly an artificial neural network. But what I do want to point out is that IBM was able to build sort of the functional modules into Watson that made it very, very good at solving those very tricky NLP processing problems. Answering these questions requires some impressive next level natural language processing. And we're closing, this is actually, Watson's now 10 years old. We've done much more impressive things since then than what Watson did. So trying to soften you up to the idea that some machine might soon solve the problem we're considering. Okay, so in conclusion, I'm suggesting that an artificial neural network might pass the robust Turing test. There are some indications with developments in artificial neural networks and the capacities that they are demonstrating that we will soon, 20 to 50 years, depends on who you talk to, be able to build an ANN system that will pass even the modified, harder Turing test that we've had in mind. And that means we're going to have to decide what we think about the implications of that and answer all of these Turing and Turing related questions. Now that's a dodge, that comment. But what I'm suggesting is, look, it's starting to look like that sort of thing, we ought to call that thing conscious. Or if not, we need to get clear on why not. And we don't want to just be sort of human chauvinist about it. We don't want to just say it's not conscious because it's not made of human meat. We want to have good philosophically principled grounds for saying that it's not thinking or it's not conscious or it doesn't understand. So what are those grounds? What are legitimate philosophically significant objections that you might pose to something that could perform those kinds of tasks? All right, that's it for my second lecture on the Turing test.